All right. So this practice quiz is the solutions guide to the practice quiz is going to go through the entire thing. Some things I've pre-populated, but other things, and we'll talk about, but other things we'll work through together. So the first thing we're supposed to do is rank the intermolecular forces from strongest to weakest. The strongest here would be ion-ion attractions. The second strongest would be hydrogen bond forces of attraction. The third strongest would be dipole-dipole forces of attraction, and the fourth strongest would be London dispersion forces of attraction. Which intermolecular force can a nonpolar covalent molecule have? A nonpolar covalent molecule will have London dispersion forces only. And what are the qualifications a molecule has to have in order to have hydrogen bonds? It needs to be a polar molecule, and it needs to have a hydrogen bonded to an oxygen, a hydrogen bonded to a nitrogen, or a hydrogen bonded to a fluorine. I need both of those pieces for that particular answer. So just be aware of that. The second thing that we needed to do for this practice quiz is identify the intermolecular forces present and then show the interaction between the molecules. So in this case, I identified this to be LDF, London dispersion force, because it's a molecule, there's no metal present, and dipole-dipole because there's no hydrogen bonded to that nitrogen. When I drew the structures attracted to one another or showing the force of attraction, I showed one of the positive iodines being attracted to one of the negative nitrogens. Now, the next example here, some students might have found or might think is like meant to be a trick, but it's really not. In this next example, we're talking about this being London dispersion forces only. And so the reason why I want to make a point or at least show this is that in this example, all of the electrons are being pulled away from carbon, right? So they're being pulled away from carbon to the same type of element, which in this case is chlorine. So even though there's a bunch of polar bonds here, the polar bonds are pulling across from each other and cancel each other out. And when they pull across from each other and cancel each other out, that makes this molecule nonpolar, which means the only type of intermolecular force of attraction it can have is London dispersion forces. So we draw it in a circle. We make one side arbitrarily delta negative, the other side arbitrarily delta positive, and then show the force of attraction in between. Questions? In the next section, you are asked to identify which one of these the following substances would have a higher boiling point. And the correct answer here for your claim is going to be CH3NH2 will have a higher boiling point than CH3CH3. The evidence that you could provide is CH3NH2 has London dispersion forces, hydrogen bonding, and dipole-dipole intermolecular forces of attraction, while CH3CH3 only has London dispersion forces. The reasoning that you're going to want to be able to provide is that CH3NH2 has more and stronger intermolecular forces of attraction and will require more energy to overcome those forces of attraction. So for a complete credit, I need you to tell me in your reasoning that the intermolecular forces are stronger and that they will require more energy to overcome those forces of attraction. So I need both of those pieces. Questions? Okay. Here's one that we will work out together as a team, and I've done some of the pre-work. But in reality, you're asked to calculate the amount of energy needed to raise the temperature of 500 grams of silver from 150 to 450 degrees Celsius. So in this problem, we are going to substitute our values in. I know that the mass is 500 grams. I know that the specific heat. Now, because we are going from 150 to 450, that leads me to believe that we're not quite to the melting point yet. So that means that we're going to deal with a specific heat, which in this case is a solid, and that's the only one that you're given. So it's 0.235 joules per gram per degree Celsius. And now the TF and the TI, I've already identified the final temperature to be 450 degrees Celsius minus the initial temperature, 150 degrees Celsius. I'm going to grab my calculator and take 500 times 0.235 times 450 minus 150, and I get a value for the heat added to be something like 35,250 joules. Sig fig wise, we need to have three significant figures here because 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So that 5 rounds that 2 up. So my final answer is going to be 35,300 joules. Some people earlier today converted that to kilojoules, and that would be like 35.3 kilojoules. I will take both answers, but we're going to keep. But any questions about this? We're going to try to keep rolling here. Now we're going to talk about acetone, and in this case, we're talking about heat absorbed. So heat absorbed in this case tells me that energy is going in to the system when 0.88 grams of acetone evaporates. So I'm going to go from mass to mole to energy here. And so I'm going to start with my 0.88 grams of acetone, which is C3H6O. And I'm going to go mass to mole to energy. I need to calculate the molar mass. So I have 3 carbons times 12.01, which is 36.03. I have 6 hydrogens times 1.01, which is 6.06. And I have 1 oxygen times 16. So that's 16. I add that up, and I believe that that's 58.9. I believe that's 58.9. 0.09. I lied. 0.09. So that's going to go on the bottom, my 58.09 grams of C3H6O, and 1 mole of C3H6O will go on top. In this case, because we are evaporating, that means that we need to use the heat of vaporization. Now, because energy is being absorbed or added in, that means delta H needs to be positive. So I'm going to take the 30.2 kilojoules, and that's in 1 mole of C3H6O. Grab my calculator, 0.88 times 30.2 divided by 58.09, and I get something like 0.457496 something. This problem here has 1, 2 sig figs, 1, 2, 3, 4 sig figs, 1, 2, 3 sig figs. So my final answer has to have 2 sig figs. So that 7 will round that 5 up. So my final answer is going to be 0.46, and that will be kilojoules of energy, like so. Questions about this? All right. My next section is given a situation, identify if something is endothermic or exothermic, and explain. Sample of solid silver is heated at negative 94 until it turns into a liquid. So it's going from a solid to a liquid. So that means that we're adding energy. So when you add energy, that means that it is endothermic. So an endothermic reaction. Okay, so now my explanation of answer, and I need you to tell me 2 things. I need to tell you what's going on with the heat or energy. In this case, heat or energy is being added. And then I also need to tell you I need you to tell me what is going on a particle level. In this case, the intermolecular forces of attraction are being weakened as the solid turns into a liquid. In the case of the second one, I have a container of acetone and I'm just heating it. So it's just getting warmer. but heat is definitely being added, so that is endothermic. And I'm going to say it's endothermic because heat or energy is being added. And the other part of this that I need you to tell me about is that the particles are now moving faster. Okay, it's not evaporating yet. It's just the particles are moving faster. So there's the heat and energy portion of this and what's going on a particle level. Questions? Now this next one here is going to require some time. So what I'm going to do is I'm going to skip it and come back to it. And I'm going to show you the last page or the last portion of this real quick once. And then we'll come back so we can get through H7. So in this example here, the temperature of the normal melting point, according to the graph, remember your normal melting point is going to be always associated with 1 atmosphere. So I'm going to go straight across. I'm going to drop that one down, and that's pretty close to 100 degrees Celsius. The line that best describes the equilibrium between a solid and a gas, the solid, my solid line here, or my solid barrier here, and my gas barrier here. So it has to be BD. Yes, sir? 100 degrees Celsius would be the best one, because I do tell you it's degrees Celsius. Okay. And then lastly, what is the temperature and pressure of the triple point of this graph? The triple point is at point B on this graph. And so I went over and down, and I found out that it was about 90 degrees Celsius and about 0.65 ATM. And I would like to point out that as long as your answer is reasonable, I will accept it. Yes. Yes. All right. So now I'm going to go back and I'm going to do this problem as best as I can with our time remaining. Yes, you could definitely put 0.70. All right, so the first thing that I've done here is I went through and identified my melting point, my freezing point, and I added it to my graph. Ideally, this would have been like more in line with that. I don't know what happened there. The next thing I'm going to do is I'm going to remind myself that on this graph, this would be solid, this would be liquid, and this would be a gas. I would go to remind myself that this would be a melt, and this would be a freeze, and this would be a boil, and this would be a condense. And then in this case, oh, look at how nice we were. We told you that you're going to be liquid starting at liquid acetone at 45 degrees Celsius. So that means I'm going to be somewhere in this ballpark at 45 degrees Celsius. And you're going to frozen acetone. That should tell you you're going to a solid at negative 98.6. So somewhere down here, you'll be negative 98.6. So that tells me that in this problem, I'm going to go from a liquid to a solid. And the way to get there is I have to do a freeze first. And when I do that, there's a couple of things that I need to remember. I'm going to have to do a thermal calculation. I'm going to have to do a phase calculation. And I'm going to have to do a second thermal calculation. The other thing I want to point out is the direction of our graph is going down. Like the direction of that we're traveling temperature-wise is going down. So that means that energy is releasing or released. So that means that the delta H has to be negative. All right, so to do the math as best we can, we have Q is equal to mass times specific heat times TF minus TI, where in this problem, our mass was given to us as 24 grams. And we know we're in a liquid, so we're going to use that specific heat, which is 2.22 joules per gram per degree Celsius. And our temperature, our initial temperature is going to be the 45.2. Our final temperature for this one is going to be the melting point or freezing point, which is negative 94. So that means this is going to be negative 94.9 degrees Celsius minus 45.2 degrees Celsius. So I'm going to throw that in the calculator. 24 times 2.22 times negative 94.9 minus 45.2. And I get a value here to be somewhere around negative 7,464.52 joules. I'm going to convert that to kilojoules right away. And I get something like negative 7.4. We need 3 sig figs here, so we're going to say 6 kilojoules. My next calculation is my phase calculation. And remember, we're freezing. So this is going to be the 24.0 grams of acetone, which is C3H6O. We are going to go mass to mole to energy. So mass to mole to energy. We've already calculated the molar mass of this one up above, so I'm going to go back up and grab that. Oh, look, it's 58.09 grams, so I'm going to use that one right here. 58.09 grams of acetone in 1 mole of acetone. And because we're freezing, we need to use the heat of fusion here. And because we've already decided that energy is being released, it must be negative. So this is going to be a negative 5.69 kilojoules in 1 mole of acetone. So 24 times negative 5.69 divided by 58.09 gives me like negative 2.35. That's the number of sig figs we need, kilojoules. The last calculation that we have, well, not the last, but one of the last calculations that we have to do here is another thermal calculation, which, as you may recall, is Q is equal to mass times specific heat times TF minus TI. In this case, Q is going to, or mass is going to still be 24.0 grams, but now we're going to use the specific heat for a solid because that's where we're at. So that's going to be 1.65 joules per gram per degree Celsius. And my TI this time is going to be my melting point, which is negative 94.9. And my TF is going to be my final destination here, which is going to be negative 98.6 degrees Celsius minus negative 94.9 degrees Celsius. So when I plug this into my calculator, I get 24 times 1.65 times negative 98.6 minus 0.6 minus negative 94.9. And I get something like for Q to be negative 146.52 joules, which I'm going to convert to kilojoules. 1 kilojoule is 1,000 joules, and that becomes negative 0.14, let's say 7 kilojoules. The last thing that you have to do is you have to add all of this business up. So I'm going to add the negative 7.46 kilojoules plus the negative 2.35 kilojoules plus the negative 0.147 kilojoules. So negative 7.46 plus negative 2.35 plus negative 0.0147 with the appropriate number of significant figures becomes, I believe, 9.9. I think I calculated this something wrong here. So it becomes negative 9.96, I believe, kilojoules is your final answer. And we'll check that in a second. But that is the solutions to your practice quiz.